Video, what we're going to do is talk a little bit about the electric field and summarize a lot of the results that we have developed over the course of the semester. So the thing that really has driven the development of electricity and magnetism for us has been this idea that matter has charge. And one of the core ideas that we developed in this course is that charge generates electric field. So when we have some bit of charge sitting around, what we observe is that it creates this thing called the electric field, and that can interact with other charges. What we started with was the idea of a single point charge, so something that looks like this, that will generate an electric field all of space, and that charge generates an electric field that we modeled using the point charge equation, namely 1 over 4 pi epsilon naught q over r squared r hat. Now, the really cool thing about the electric field is that it obeys a principle called superposition. This is something that we studied in a lot of detail. So a lot of times, when we're looking at real physical situations, we don't have a single charge sitting around like this. We have a bunch of charge sort of smeared out over some larger piece of matter. And so the question for us becomes, well, how do we deal with that? Well, superposition allows us to deal with it by saying if we're interested in the total field, which we called the net electric field, we simply just add up the field due to every little piece of the material. So this is like adding up a bunch of little point charges. Now, we started with this idea by looking at discrete charges, but if you have a continuum like this, if you have some piece of matter that has charge sort of smeared out all over the place, the idea is still very similar. We treat each little piece as having a small amount, or contributing a small amount of electric field, which is modeled by a point charge, 1 over 4 pi epsilon naught dq over r squared r hat. Namely that the small amount of charge that lives in some little space right here contributes an electric field, of dE over here. And all we've got to do then is superpose it. We just got to add it up. The way we add it up is using an integral. So if we want to know the total electric field that's a result of some continuous distribution of charge, we integrate that electric field. We did that for a ring, we did that for a line, we did it for a plane, right? So essentially what we're doing is just adding up all the contributions from all the little pieces of charge. Now, this summarizes a lot of what we know about the electric field, but one of the things that we're really interested in is how does this electric field then interact with other pieces of material, right? So one of the things that we go out and we observe is that if we bring some electric charge near other charged objects, other things that have electric charge, then there's a force that one experiences due to the other. And that electric force is related to the total amount of charge and the net electric field that is at the location of that charge. So for example, we have some chunk of material, and we want to know the force that this charge experiences. We add up to find the total electric field at the location of this charge. So maybe it points like this. And then we multiply that charge times the electric field to find what the interaction is, what the force is. Now that force might be attractive, it might be repulsive. It will depend entirely on the sign of this charge to tell us whether it gets pulled towards the material or pushed away from it. This has some implications for us. Namely that we can have a situation where something will polarize. So the example that we had was that if we bring up a piece of material, so let's say it's a metal, and we bring some big positive charge nearby this metal, then the electrons that are in the metal are going to shift towards that positive charge. They're going to show up over here, and they're going to leave behind positive nuclei on the right-hand side. This polarization effect happens in metals. It also happens in plastic materials, right? And we had sort of a drawing that looked more like this. which told us that the electrons don't move all the way over, they just shift a little bit, right? And so this effect of polarization has a lot of really useful properties in that we can sort of change the distribution of charge in different kinds of materials. Now the last thing we'll talk about in terms of the electric field is how it affects situations where we have circuits. So if a charge experiences an electric field, it is going to feel a push. And so in our discussion of circuits, which we will draw sort of like this, these big thick wires, and here's a battery. So this is the positive side of the battery and the negative side of the battery. What we found was that to drive the current around, to drive the electrons around this circuit, we had to have an electric field that existed in the wires. That electric field pointed from the positive side of the battery to the negative side of the battery, like this. That would be the electric field inside the wire. And it was a result of a redistribution of charge along the surface of the wire. So there'd be a lot of positive charge that we collect over here, a little less positive charge over here, maybe no charge on the surface of the wires there, maybe a little negative charge here, and a lot more negative charge there. That gradient of surface charge is actually what creates that electric field that exists inside this wire and pushes the electrons around in the opposite direction. They feel a force that is opposite the electric field. So this concept of the electric field is incredibly useful. It applies in lots of different places, not just pushes and pulls between charges, but also how materials polarize and how currents can actually run through circuits.